In September 1977, a rocket lifted off from Cape Canaveral. On board was a spacecraft weighing about 825 kilograms. Not the largest ever launched, not the most powerful, not even the most technologically sophisticated by the standards of its time. Its onboard computer had less processing power than a modern pocket calculator. Its 3.7-meter antenna transmitted data to Earth at speeds that today seem almost comically slow. But this spacecraft is still in flight. Right now, as you read this, Voyager 1 is traveling through space beyond the boundaries of our solar system. It has moved farther from the Sun than any other human-made object in history. It crossed the heliopause, the boundary where the solar wind stops and interstellar space begins, and is now travelling through the space between stars. Interstellar space, literally between the stars. This is the farthest any human technology has ever reached, and the spacecraft is still working, still transmitting signals, still talking to us across a distance that light takes more than 22 hours to cross. Tonight we're going to follow this story honestly, not just as a triumph of engineering, though it is exactly that, but as something more personal, as a story about loneliness and distance and time, about what it means to send something so far away that communicating with it becomes an achievement in itself, about what waits for Voyager in the future through thousands and millions of years when its story continues without us. If the night is long, stay. Let us begin with how Voyager 1 came to be where it is now, with the rare planetary alignment that opened the window for this mission. Once every approximately 175 years, an event occurs that astronomers call the Grand Alignment. All 4 giant planets, Jupiter, Saturn, Uranus and Neptune, occupy positions relative to the Sun where a so-called gravitational slingshot or flyby acceleration is possible. A spacecraft launched at the right time on the right trajectory can use the gravity of each planet as a slingshot, accelerating and changing direction through the gravitational attraction of the planet, in essence stealing a tiny fraction of its orbital angular momentum. This alignment occurred in the late 1970s and early 1980s. The next will be around 2153. Missing such a window would mean waiting another 175 years. NASA did not miss it. In 1972, engineer Gary Flandreau at JPL, the Jet Propulsion Laboratory, first calculated the possibility of using this alignment to send a spacecraft to all the outer planets. This was a conceptual revolution. Before this, a journey to Neptune had seemed practically impossible because of the required propellant and time. With gravitational assists, possible. The original plan was the Grand Tour, 4 spacecraft to 4 planets. Budget constraints reduced the program. In the end, 2 spacecraft were launched, Voyager 1 and Voyager 2, both in 1977. Voyager 2 first, on August 20th. Voyager 1 on September 5th, 16 days later, but on a faster trajectory. Voyager 1 received its name not by launch date, but because it was first to reach Jupiter and first to pass Saturn. Let us talk about the trajectory, about how exactly Voyager 1 travelled from Earth to the boundaries of the solar system. Launch in September 1977. Velocity at departure from Earth's gravity, sufficient to completely escape Earth's gravitational pull and enter a heliocentric trajectory, not into orbit around Earth, but directly toward Jupiter. First encounter, Jupiter. Voyager 1 reached Jupiter in March 1979. 18 months after launch. This was the first close look at the planet in detail impossible to see from Earth. Images of the Great Red Spot from a distance of a few 100,000 kilometers, a swirling atmospheric structure larger than Earth. The discovery of active volcanoes on Io, the first detection of active volcanism beyond Earth. Detailed images of Europa showing a surface cut with fractures, hinting at a subsurface ocean. The gravitational slingshot at Jupiter accelerated Voyager 1 and redirected its trajectory, aimed towards Saturn. Saturn. Voyager 1 reached Saturn in November 1980. Again, detailed images, new discoveries. Saturn's rings turned out to be a significantly more complex structure than assumed, thousands of individual ringlets and gaps. Saturn's atmosphere, with characteristic bands and storms. Saturn's moons, 23 observed during the flyby. But the most important object at Saturn turned out to be Titan. Voyager 1 was given the assignment: fly as close as possible to Titan, the only moon in the solar system with a dense atmosphere. This assignment changed the trajectory of the mission permanently. For a close flyby of Titan, the trajectory had to be altered in a way that made a further flight to Uranus and Neptune impossible. This was a deliberate sacrifice. Voyager 1 gave up the possibility of further planetary encounters for Titan. Voyager 2 would go to Uranus and Neptune. After Saturn, Voyager 1 departed upward above the plane of the ecliptic at an angle of about 35 degrees and began moving away from the Sun, a journey that continues to this day. The results of the Titan flyby were worth this sacrifice. Titan's atmosphere proved to be dense and rich in organic molecules, nitrogen and methane. Opaque in visible light, Voyager 1 could not see the surface, but measurements of atmospheric composition showed that Titan was an anomalously interesting object. This foreshadowed later discoveries of the Cassini-Huygens mission. After Saturn, Voyager 1 continued moving away from the Sun. Without another planned planetary encounter, simply forward, into space. Let us now talk about what happened aboard Voyager 1 over the following decades, about the gradual shutdown of systems as the spacecraft moved farther away and its nuclear batteries weakened. Voyager 1 is powered by 3 radioisotope thermoelectric generators, RTGs. They use the heat from the natural radioactive decay of plutonium-238 to generate electricity. No moving parts, no fuel that needs burning, just the gradual decay of plutonium nuclei releasing heat. At launch, the RTGs of Voyager 1 produced about 470 watts of electrical power. Plutonium-238 has a half-life of about 87.7 years. This means that approximately every 88 years, the RTG power decreases by half. By now, about 47 years after launch, RTG power has dropped to approximately 250 to 270 watts. Still sufficient for several instruments to operate, but each year there is less. NASA gradually shut down instruments as power decreased. The scan platform actuators shut down. The photopolarimeter shut down. The planetary radio astronomy system shut down. The imaging system, yes, Voyager 1's cameras were turned off in 1990 after the famous pale blue dot image sequence to conserve energy for the scientific instruments still operating today. Currently, 4 main scientific instruments are operating: the magnetometer, the low-energy charged particle detector, the cosmic ray detector, and the plasma wave system. These are transmitting the data that launched a revolution in understanding the heliopause and interstellar medium. By NASA engineers' estimates, Voyager 1 will be able to sustain at least one scientific instrument until approximately the end of the 2020s. After that, the RTG power will be insufficient. The spacecraft will continue moving, but without active scientific instruments. It will fall silent. Let us now talk about the most significant discovery of Voyager 1, about the crossing of the heliopause and entry into interstellar space. The heliosphere is the region of space dominated by the solar wind. The Sun constantly ejects a stream of charged particles, primarily protons and electrons, called the solar wind. This wind propagates in all directions from the Sun, gradually losing density with distance. At some distance, the pressure of the interstellar medium balances the pressure of the solar wind. This boundary is called the heliopause. Voyager 1 crossed several structural boundaries of the heliosphere. The first, the termination shock. The solar wind travels supersonically, faster than the speed of sound in plasma. Upon encountering the outward pressure of the interstellar medium, it abruptly slows, forming a shock wave. Voyager 1 crossed the termination shock in December 2004 at a distance of about 94 astronomical units from the Sun. The second boundary, the heliopause itself. Beyond the termination shock lies a region called the heliosheath, where the slowed solar wind continues to interact with the interstellar medium. In August 2012, Voyager 1 crossed the heliopause at a distance of about 121 astronomical units. August 25, 2012, the date later recognized as a historic moment. On that day, Voyager 1 became the first human-made object to exit the heliosphere, to enter interstellar space. How was this determined? Through several indirect measurements. Voyager 1's plasma detector had failed in 1980. Direct measurement of plasma parameters was not possible. But the magnetometer and charged particle detector continued working. In August 2012, data from these instruments showed a sharp change. The flux of solar system charged particles, called anomalous cosmic rays, dropped sharply. The flux of galactic cosmic rays rose sharply. The direction and intensity of the magnetic field changed. This was the characteristic pattern of transition from one physical environment to another. Nevertheless, recognition of this fact was not immediate. There was debate about whether the observed change was actually a heliopause crossing or some intermediate structure. In 2013, observation of plasma waves induced by solar events provided additional evidence. The plasma density around Voyager 1 corresponded to interstellar rather than heliospheric conditions. This definitively confirmed it. Voyager 1 is in interstellar space. Let us now talk about the specific measurements Voyager 1 is transmitting from interstellar space right now, because this is not just a historic achievement, but active science. The magnetic field. In the heliosphere, the magnetic field is oriented at an angle determined by Earth's orbit around the Sun. The Sun's field winds into a spiral as the Sun rotates. In interstellar space, the situation is different. Here, the interstellar magnetic field of the galaxy dominates. Voyager 1 measures this field with unprecedented precision, directly in a place where no other instrument has ever been. Magnetometer data showed something unexpected. The magnetic field of the interstellar medium near the heliopause turned out to be oriented nearly parallel to the heliospheric field at the same boundary, which did not match some theoretical predictions. This is valuable information about how the heliosphere interacts with the surrounding galactic environment. Galactic cosmic rays. Voyager 1 measures the flux of high-energy particles arriving from the depths of the galaxy. Inside the heliosphere, the Sun partially shields Earth and the inner planets from these particles. The solar wind creates a so-called magnetic shield effect. Beyond the heliopause, this shielding is absent. Voyager 1 measures the raw galactic cosmic ray flux. These measurements are important for understanding the radiation environment in deep space. Critically important information for planning future crewed, interplanetary or interstellar missions. Plasma waves. When the Sun produces large ejections, coronal mass ejections, a wave of disturbance propagates through the heliosphere and eventually reaches Voyager. Even in interstellar space, sparse plasma responds to these disturbances. Voyager 1's plasma wave system detects these low-frequency waves. It was through them in 2013 that interstellar plasma density was measured, about 0.06 electrons per cubic centimetre. This seems unimaginably small, and it is. Interstellar space is almost perfect vacuum by any earthly standard. In the best laboratory vacuum chambers on Earth, about 1 billion molecules per cubic centimetre. In interstellar space, about 0.06 particles. Each of these measurements is a concrete contribution to science. Data that cannot be obtained any other way because no other instrument has ever been there. Let us now talk about communication with Voyager 1, about how exactly we are still talking to a spacecraft so far away. The signal from Voyager 1 travels to Earth in more than 22 hours in one direction. This means that any command sent from Earth reaches the spacecraft after 22 hours. A response or confirmation comes back another 22 hours later. One exchange takes more than 2 days. The signal is transmitted at approximately 8.4 GHz, the X band. The spacecraft's 3.7-meter antenna is directed with sufficient precision to reach the receiving antennas of NASA's Deep Space Network, DSN. DSN is a global network of enormous radio antennas located at 3 sites around the world. At Goldstone, California, in Madrid, Spain, in Canberra, Australia. Placement at 3 sites, separated by roughly 120 degrees of longitude, ensures continuous tracking of the spacecraft, regardless of Earth's rotation. When one antenna drops below the horizon, another picks up the spacecraft. DSN antennas used to track Voyager use dishes 34 and 70 meters in diameter. The 70-meter antenna at Goldstone is one of the world's largest. It receives a signal whose power, by the time it arrives at Earth, is about 0.000000000000002 watts. About 2 times 10 to the minus 20 watts. Roughly 1 trillion times less than a faint nightlight. This is not an error or an exaggeration. The power of Voyager 1's signal reaching Earth is about 2/10 of an attowatt. And yet our antennas receive it. And yet we extract real scientific data from this signal. This itself is one of the most astonishing engineering achievements in human history. Not just creating a spacecraft that works for 47 years in space, but creating a communication system that receives a signal of a fraction of an attowatt from a distance of more than 22 light hours. In November 2023, an event occurred that almost severed contact with Voyager 1 permanently. In the Flight Data System Computer, FDS, a failure occurred that caused the spacecraft to begin transmitting unreadable data. For several months, NASA engineers received no coherent telemetry from Voyager 1. Diagnosing the problem through a communication system with a 22-hour one-way delay is an extraordinarily difficult task. Each attempt to send a diagnostic command required waiting 44 hours to see the result. Engineers, many of whom specifically studied archived project materials from the 1970s because the original team was no longer working, gradually worked out the problem. It turned out that part of the FDS memory was damaged, probably from the impact of a high-energy particle, a cosmic ray. The code that was supposed to execute was partially written into the damaged memory section. The solution? Move this code into other working memory sections. In April 2024, NASA restored full communication with Voyager 1. The spacecraft is once again transmitting readable scientific data. Contact restored. This event is remarkable not just as an engineering story. It shows how fragile this link is. One damaged memory section, one cosmic ray hitting the right spot, and we almost lost Voyager 1 forever. And how great was the will and competence of the engineering team to restore it. Let us now talk about what it is like to work as a Voyager engineer in 2024, about the people who talk to the most distant human-made object. Most of the engineers who built Voyager 1 are retired or have died. The program is 47 years old. The people who built the onboard computers, who designed the instruments, who wrote the original flight code, these are people now in their 70s, 80s and 90s. Or they are gone. The team currently working with Voyager is small, a few dozen people at JPL. Many of them joined the project long after launch. They studied original technical documentation, some of which exists only in paper archives because the data formats of the 1970s are incompatible with modern computers. Working with Voyager in 2024 is partly working with a historical relic, partly working with a living system that continues to produce data, partly working with hardware and software that requires deep understanding of engineering principles from half a century ago. When the FDS memory failure occurred in November 2023, part of the diagnosis required consulting veterans of the project who had long since retired. People who remembered why certain decisions were made in the 1970s, why the code was written exactly this way, why the memory architecture was structured exactly so, were invaluable resources, the living memory of the project. With every year, fewer such people remain. When the last of them is gone, understanding of Voyager will exist only in documents. Fortunately, many documents were preserved. Unfortunately, some exist in formats that are difficult to read without special equipment. This is one of the most unusual forms of institutional memory that humanity faces. Not just we remember how this works, but we need to remember how this works, because it is working right now at a distance of 22 light hours from us, and we cannot go there to fix it. Let us now talk about where exactly Voyager 1 is in space, not just far, but specifically. Right now, Voyager 1 is at a distance of about 23.5 billion kilometers from the Sun. This is about 157 astronomical units. For scale, Earth is 1 astronomical unit from the Sun. Pluto averages about 39 astronomical units. Voyager 1 is 4 times farther than Pluto. Light from the Sun reaches Earth in about 8 minutes. To Voyager 1, more than 22 hours. The spacecraft is moving at about 17 kilometers per second relative to the Sun, about 61,000 kilometers per hour. Fast by any human standard, but incredibly slow relative to interstellar distances. The nearest star, the Alpha Centauri system, is about 4.37 light-years from the Sun. At Voyager 1's current speed, it would take about 73,000 years to cover that distance. And Voyager 1 is not flying toward Alpha Centauri, it is flying in a different direction, toward the constellation Ophiuchus. In about 40,000 years, Voyager 1 will pass at a distance of about 1.7 light-years from the star Gliese 445 in the constellation Camelopardalis. This is not a flyby in any meaningful sense. The distance is more than 400 times the Earth-Alpha Centauri distance. Simply the nearest stellar neighbour along this path over the next tens of thousands of years. In millions of years, Voyager 1 will continue moving through the galaxy. Gravitational interactions with passing stars will gradually change its trajectory. On timescales of billions of years, it will be a participant in galactic dynamics on equal terms with any other star or planet. This is one of the most striking facts about Voyager 1. It will not stop. In interstellar space, there is no significant deceleration, no air, no friction. The spacecraft will continue its journey indefinitely, or until it is captured by the gravity of some object or destroyed by collision. Statistically, the chance of collision with any significant object in interstellar space over millions of years is vanishingly small. Interstellar space is almost perfectly empty. Voyager 1 will most likely travel through the galaxy virtually forever, at least on timescales incomparably exceeding the existence of our civilization. Let us now talk about what is aboard Voyager 1 beyond the scientific instruments, about the Golden Record and what it says about the intentions of the people who created it. On each of the two Voyagers is a golden phonograph record, not metaphorically, literally a gold-plated copper disc 30 centimeters in diameter. On it are recorded sounds and images intended to give some future observer, possibly an extraterrestrial civilization, a sense of Earth and its inhabitants. The record contains 116 images encoded in analog format. Among them, mathematical definitions, anatomical diagrams of humans, photographs of Earth from space, scenes of life from different cultures, animals, plants, landscapes. Instructions for playback are encoded on the record itself, in the form of a diagram showing how to use the included stylus for reading. The record contains sounds of Earth, ocean surf, rain, thunder, wind, the cry of a whale, birdsong, frogs, crickets, a newborn's cry, human laughter, footsteps, human heartbeat, and music. 90 minutes of music from around the world. Bach, Mozart, Beethoven, Chuck Berry's Johnny Be Good, Georgian polyphonic chanting, Indian classical music, Javanese gamelan, Mexican music, Australian aborigines, Peruvian flutes, Bulgarian folk singing, Senegalese drums, Japanese koto, Azerbaijani mugam, greetings in 55 languages, in Russian, Chinese, Arabic, Swahili, Hindi, Latin, Welsh, in 55 languages of human speech. A message from UN Secretary-General Waldheim, a message from President Carter. All of this placed in an aluminium case that protects the disk from interstellar erosion. By physicists' estimates, the record will remain in recognizable condition for more than 1 billion years. 1 billion years. For comparison, modern Homo sapiens has existed for about 300,000 years. Writing, about 5,000 years. Our civilization in its current form, a few hundred years. The golden record will outlast all of this with enormous margin. If in 1 billion years some intelligence finds Voyager, the record will contain information about us, about what we were, about what we heard and what we found beautiful. This is the most durable work of human culture ever created. Books decay, stone crumbles, metal structures corrode. Voyager's golden record in interstellar space, protected from oxygen, from moisture, from biological processes, will outlast everything. Carl Sagan led the creation of the record. He described it as a message in a bottle thrown into the cosmic ocean. The chances that it will ever be found and deciphered by an intelligent being are vanishingly small. Interstellar space is vast. Voyager is small. The probability of accidental discovery without deliberate search, practically zero. But this is not the main point. The main point is that we tried. That in 1977, a group of people sat and thought, what do we want to say? Who are we? What do we love? What moves us? And tried to answer this question in a form that might be understandable to a being about which we know nothing, neither its physiology, nor its perception, nor its system of concepts. This is one of the most human acts we have ever performed in space. Not resource extraction, not military advantage, not economic benefit. Simply the desire to say, we are here, we existed. This is what we heard in our world. Let us now talk about the specific historic moment that is one of the most significant in Voyager 1's history. About the photograph called Pale Blue Dot, taken on February 14th, 1990. By February 1990, Voyager 1 was at a distance of about 6 billion kilometers from the Sun, roughly 40 astronomical units. Its cameras were about to be turned off, permanently. They had already completed all planned science, and keeping them operational required electrical power needed by other instruments. Carl Sagan insisted on one final use of the cameras. He proposed, and succeeded in having the idea accepted despite bureaucratic resistance, turning Voyager 1's cameras back toward the Sun and taking a series of photographs of the entire solar system, a family portrait, as it was called. On February 14th, 1990, Voyager 1 executed this sequence of images. 60 frames covered most of the solar system. On one of these frames, shot at a specific angle where scattered sunlight filled part of the frame, a tiny speck was visible, less than 1 pixel in size, pale blue. This was Earth. All continents, all oceans, all 5.5 billion people living in 1990. Everything that had ever happened in human history. All wars, all discoveries, all works of art, all the great civilizations of the past and present, compressed into less than 1 pixel in a photograph. Sagan wrote about this image a text that became one of the most quoted in the history of scientific literature. He wrote about the pettiness of human pretensions to greatness, about the absurdity of human conflicts, about the responsibility of people to care for the only home we know in the vast cosmic darkness. After this image, Voyager 1's cameras were turned off permanently. No more photographs, only instrument data, only numbers. But that single photograph, that pale blue dot, remained, and will remain for a long time. Let us now talk about something that is rarely examined in the context of Voyager, about loneliness. Not metaphorical, but literally physical loneliness of the spacecraft in space. Voyager 1 is the only human-made object in that region of space where it currently is. The nearest human-made object to it, Voyager 2, is billions of kilometers away in a different direction. The nearest star to it, the Sun, is more than 22 light-hours away. Within a range of trillions of kilometers from Voyager 1, there is nothing except sparse interstellar gas, less than 1 atom per cubic centimeter, and occasional dust particles. Not a single rock, not a single meteorite, not a single asteroid. Nothing large enough to be visible in a telescope. Just space. Nearly perfect vacuum. Nearly absolute darkness. The Sun is simply another bright star, noticeably brighter than the others, but not bright enough to provide significant illumination. Stars around it, non-twinkling points in absolute darkness, as they always appear in interstellar space without an atmosphere. This place has no reference points except the starry sky. No surface, no horizon. Nothing in the immediate vicinity. And in this space, a small spacecraft the size of a small car, moving at 17 kilometers per second, continuing to measure its environment, continuing to transmit data on a 23-watt signal that by the time it reaches Earth will have weakened by trillions of times. The word lonely usually describes an emotional state. A spacecraft does not experience emotions. Voyager 1 is not lonely in the sense a person is lonely. But if you were to describe the physical reality of Voyager 1 in one word, the word lonely fits better than any other. The most distant, the most isolated, the most removed from everything we call home or surroundings or neighborhood. A solitary object. And yet not silent, still speaking. Let us now talk about the concrete science of interstellar space that Voyager 1 discovered and that changed our understanding of where the solar system ends. Before Voyager, theoretical models predicted the existence of the heliopause, but its exact location, structure, and properties were unknown. Different models gave different predictions. Some predicted the boundary was closer, around 80 to 90 astronomical units. Others farther, around 150 astronomical units. Voyager 1 crossed the heliopause at about 121 astronomical units. This gave the first direct measurement of the actual location of the boundary, at least in one direction. But this is one measurement point. The heliosphere is not a perfect sphere. Its shape is determined by both the solar wind, which varies depending on solar activity level and slightly by direction, and the pressure of the interstellar medium from outside. Modern models suggest the heliosphere has an asymmetric shape, possibly an elongated drop with a tail on the side opposite the direction of the Sun's motion through the galaxy. Voyager 2 crossed the heliopause in November 2018, at a distance of about 119 astronomical units, roughly 2 units closer than Voyager 1 crossed in a different direction. This is important information. The boundary in different directions is at slightly different distances, confirming the asymmetry of the heliosphere. One of the most unexpected discoveries of Voyager 1 in interstellar space, the detection that the interstellar medium is significantly denser and hotter than some models predicted. The electron density of about 0.06 per cubic centimeter, higher than expected for the local interstellar medium. This suggests that our solar system is located in a bubble, the so-called local bubble, of relatively rarefied and hot plasma formed by supernova explosions in the past. The transition beyond the heliopause is a transition between conditions inside this bubble and slightly different conditions outside. Let us now talk about the golden record more specifically. about the specific choices made in creating it and what those choices reveal. The selection of music for the record was an extraordinary task. Carl Sagan, Anne Druyan, who later became his wife, and their collaborators spent months deciding what 90 minutes of human music could represent our species to an unknown listener. The choices spanned 3,000 years. The oldest piece, a Vedic chant dating to roughly the 10th century BCE, the Jat Kahan Ho by Surshri Kesar Bai Kerker, Bach's Brandenburg Concerto No. 2 in F major, Mozart's The Magic Flute, Beethoven's Fifth Symphony Cavatina, Chuck Berry's Johnny Be Good, the choice that drew some criticism, why send rock and roll to the stars? Sagan's response was characteristically direct. The kids are into it. The sounds of Earth were equally carefully chosen. Not just pleasant sounds, honest ones. Surf, rain, thunder, wind, Morse code, a train, a tractor, a horse and cart, a ship, a jet aircraft, a rocket. The sounds of human activity, including industry. The sounds of nature. The heartbeat. The brain waves of a human being, specifically Anne Druyan's, recorded while she thought of the history of the world and of love. Her brain waves are on the record. What she was thinking when those waves were recorded is documented. It is there, in the space between stars, riding on a copper disc. This is not a trivial thing. A specific human brain's electrical activity from a specific hour on a specific day in 1977, translated into a waveform, pressed into copper, gold-plated, sealed in aluminium, and now travelling through interstellar space at 17 kilometers per second. What does it mean for this to exist? We cannot fully know, but the act of creating it, the decision to try, says something about us that our other space achievements do not say in quite the same way. The record is not about capability, it is about longing. The longing to be known, to say, here is what we are, here is what we made, here is what we thought was beautiful. Let us now talk about the specific engineering decisions that have allowed Voyager to survive 47 years, because the longevity is not an accident. Every component on Voyager was chosen with enormous reliability margins. The RTGs use plutonium-238 rather than other isotopes, partly because its decay heat output is extremely predictable and long-lasting. The attitude control thrusters have been fired tens of thousands of times, and the remaining propellant, hydrazine, has been carefully managed to extend operational life. The redundant systems on Voyager were built assuming some would fail, which they have. The backup plasma detector failed in 1980. The backup radio receiver failed in 1978. The scan platform stuck briefly in 1981 during the Saturn encounter. Each failure was worked around. The engineering philosophy of that era, before the age of software-defined everything, was build it right, build it strong, assume it will work. Not because computers could monitor everything and compensate, but because the hardware itself needed to survive without intervention. The computers aboard Voyager use CMOS chips that are far less sensitive to radiation than many later semiconductor designs. The choice was partly for power efficiency and partly for radiation tolerance. CMOS was inherently more resistant to single-event upsets from cosmic rays than alternative technologies of the era. This turned out to be prescient. In interstellar space beyond the heliopause, the radiation environment from galactic cosmic rays is more intense than within the heliosphere. The fact that Voyager operated for 46 years in the heliosphere before the first significant cosmic ray-induced memory failure is evidence that the radiation tolerance of the onboard electronics was genuinely substantial. The first major computer failure from a cosmic ray hit came in November 2023, 46 years after launch. In interstellar space, where the cosmic ray flux is at its galactic maximum, that is not bad performance for hardware designed in the early 1970s. Let us now talk about the specific moment when all of this will end, about what the last days of Voyager 1's active scientific life will look like. The RTGs decay predictably. Power decreases by about 4 watts per year. The engineering team at JPL tracks this decline closely, making decisions about which instruments to keep operational as the available power margin shrinks. The last instrument to be shut down will be whichever one can be maintained with the smallest power draw at the moment when total power falls below the threshold to sustain any instruments. Current estimates suggest this will occur sometime in the late 2020s. It could be slightly earlier if an unexpected power draw from an aging system reduces the margin. It could be slightly later if an instrument consumes less power than estimated. The team will know it is coming. There will be no sudden silence. There will be a final planned shutdown of the last instrument, a final data transmission acknowledging the shutdown, and then the carrier signal will continue for some time, the raw radio transmission from Voyager with no science data in it, just the spacecraft saying, "I am here." Eventually, the carrier itself will fall below the power needed to maintain it, or the pointing will drift and the signal will fade. The DSN will continue listening for some time after the expected silence. If nothing comes, it will be declared ended. And then Voyager 1 will be a silent spacecraft moving through interstellar space. No more data, no more contact, just the trajectory, the golden record, and the aluminium casing protecting both from the slow erosion of interstellar dust and cosmic radiation. Still there, moving, just not talking anymore. Let us now talk about what comes after Voyager, about what the next generation of humanity's effort to reach beyond the solar system might look like. The Breakthrough Starshot initiative, funded by Yuri Milner and conceptually supported by Stephen Hawking before his death, proposes launching gram-scale nanoprobes accelerated by a ground-based laser array to approximately 1/5 the speed of light. At this speed, they could reach the Alpha Centauri system in about 20 years. The engineering challenges are enormous. A laser array of sufficient power would require square kilometers of area. The nanoprobes, traveling at 1/5 the speed of light, would encounter interstellar dust particles at an energy per particle sufficient to destroy the probe if the particle is large enough. Developing shielding or other mitigation is a significant unsolved problem. Transmitting data from 4 light years away using a gram-scale antenna is a fundamental communications challenge. But none of these challenges are forbidden by physics. They are engineering challenges, demanding engineering challenges, but not impossible ones in principle. The physics does not say you cannot do this. Current technology says you cannot do this. Technology changes. Nuclear pulse propulsion, the concept of propelling a spacecraft using a rapid series of nuclear explosions behind a pusher plate, could theoretically achieve speeds of a few % of the speed of light. This was studied in the 1950s and 1960s under the name Project Orion. It was never built due to the Nuclear Test Ban Treaty's prohibition on nuclear explosions in space and the atmosphere. The physics is sound. The political and environmental barriers are real. Laser sail propulsion at smaller scales, not the Breakthrough Starshot nanoprobe approach, but a larger sail and spacecraft, has also been studied. Icaros, a Japanese solar sail spacecraft, demonstrated solar sail propulsion in 2010. A laser-propelled sail would use the same principle, but with a much more intense laser source. Each of these concepts has been studied. None has been built for interstellar flight. Voyager 1, with its conventional chemical launch and gravitational assist trajectory, remains the only human technology to have crossed the heliopause. It did this accidentally, in the sense that its mission was designed for planetary science, not for interstellar exploration. Its crossing of the heliopause was a consequence of its trajectory, not a primary design objective. The next craft to cross the heliopause could be designed for this purpose, an interstellar precursor mission aimed specifically at taking measurements in the interstellar medium at greater distances and in better chosen directions. The interstellar probe concept, studied by a team at the Johns Hopkins Applied Physics Laboratory, proposes a spacecraft that could reach 200 to 400 astronomical units within 50 years, using a Jupiter gravity assist combined with a close solar flyby to maximize departure speed. Such a spacecraft could cross the heliopause in perhaps 15 years rather than the 35 it took Voyager. It could carry modern instruments capable of far more than Voyager's 1970s-era detectors. It could be directed specifically toward the nose of the heliosphere, the upstream direction, rather than the roughly perpendicular direction Voyager took. This mission has been studied and proposed. It has not been funded or approved. It awaits the decision that Voyager 1 once awaited, the decision to go. Let us talk about the specific physical environment that Voyager 1 is traveling through right now, about interstellar space as a physical object rather than an abstraction. Interstellar space is not emptiness. It is not nothing. It is matter, gas and dust that fills the space between stars. On average, across the galaxy, about 1 atom per cubic centimetre. Near Voyager 1's current location, about 0.06 electrons per cubic centimetre in the plasma component. For comparison, the air you breathe contains about 2.7 times 10 to the power of 19 molecules per cubic centimetre, about 450 billion molecules in every cubic centimetre. Interstellar space is less dense than air by about 10 to the 20 times, by 100 billion times. This is the most perfect vacuum that exists in nature, even though it is not emptiness but real matter with real physical properties. The interstellar medium consists of several components. Atomic hydrogen, about 70% of all interstellar matter by mass. Helium, about 28%. All other elements, about 2%. Molecular hydrogen, H2, primarily in dense molecular clouds. Dust, tiny particles of silicates, graphite, ice, complex organic molecules, makes up about 1% by mass of interstellar material, but plays a disproportionately important role in chemistry and star formation. The temperature of the interstellar medium varies depending on phase. Warm neutral medium, about 6,000 to 10,000 Kelvin. Warm ionized medium, about 10,000 Kelvin. Hot ionized medium, formed by supernova explosions, 1 million Kelvin and above. Cold neutral medium, about 80 to 100 Kelvin. Molecular clouds, from 10 to 50 Kelvin. Voyager 1 is currently in the local interstellar medium, in the region inside the so-called local bubble. The local bubble is a region of space about 300 light-years in diameter, where the interstellar medium is significantly hotter and less dense than the galactic average. It is thought to have been formed by several supernova explosions over the past few million years. They heated and swept away interstellar material in this region. Our solar system sits inside this bubble. Voyager 1 too is still inside it. Only after several thousand more years of travel will it exit the local bubble into denser interstellar medium, if it does at all along its specific trajectory. Inside the local bubble, the solar system is embedded in a denser cloud called the local fluff. This is a relatively small, dense cloud of neutral hydrogen through which the Sun moves at about 20 kilometers per second. Voyager is traveling through it too. This is not a romantic abstraction. This is a real physical structure that Voyager is right now traversing and measuring. Let us now talk about the legacy of Voyager 1 that extends beyond science, about what the mission has meant for how humanity understands its place in the cosmos. The pale blue dot photograph is the most powerful single artifact of this understanding. Not because it revealed new science, it did not, scientifically speaking, but because it made visceral and undeniable something that we intellectually knew but had not emotionally absorbed. Carl Sagan's text written about the photograph, which he refined for years and eventually included in his 1994 book, Pale Blue Dot, has been read by millions of people. Its core message: on this mote of dust suspended in a sunbeam, every king and peasant, every inventor and explorer, every teacher of morality, every corrupt politician, every saint and sinner in the history of our species lived out their lives. Our planet is a lonely speck in the great enveloping cosmic dark. This is not pessimism. Sagan did not intend it as pessimism. He intended it as a clarification, a way of seeing more clearly. The photograph does not make human life meaningless. It makes the specific squabbles and pretensions of human power look precisely as small as they are relative to the reality in which they occur. And it makes care for this particular dot, for this one place in an incomprehensibly vast cosmos where life that we know of has arisen, look not like sentimentality, but like rational priority. The photograph exists because Carl Sagan fought bureaucratic resistance to use Voyager's cameras one last time. It exists because someone thought it was worth doing. It continues to matter because it is true, and because the truth it conveys is one that humans, being human, tend to forget and need reminding of. Voyager 1 took this photograph. Then it flew beyond it. It is now 157 astronomical units from the dot in the photograph, travelling at 17 kilometers per second away from everything in that image. Let us now talk about the specific timeline of Voyager 1's remaining operational life, about what the coming years hold. By 2025 or 2026, the engineering team will likely need to shut down another scientific instrument to conserve power. Which one will depend on the specific power levels available and the relative scientific value of what is being returned. The cosmic ray detector and the magnetometer are currently considered the most scientifically valuable in terms of what they uniquely measure in interstellar space. The plasma wave system also provides data unavailable from any other source. The low-energy charged particle detector completes the set. Each of these four instruments tells a different part of the story of interstellar space. As power decreases, the team will make the most difficult kind of scientific triage, choosing which part of the story to preserve and which to lose. By the late 2020s, perhaps 2028 or 2029, though the exact date is uncertain, only one or perhaps two instruments will remain active. The final days of active science will be marked by the shutdown of instruments one by one over months or years. The final instrument shutdown will be planned as far in advance as possible, not because a surprise ending would be less meaningful, but because planned shutdowns allow the maximum amount of science to be extracted from each instrument's final hours of operation. Sequences can be optimized, data can be prioritized. The last measurements can be directed at whatever is most scientifically valuable in Voyager's immediate environment at that moment. Then silence. The carrier signal, Voyager transmitting without any science instruments active, may persist for some time after the instruments shut down. A radio signal from a spacecraft that has run out of science to do, but still has enough power to say, "I am here." Eventually, that too will fade. And then Voyager 1 will be the most distant, silent artifact of human civilization. A gold-plated copper record embedded in a metal spacecraft moving through interstellar space at 17 kilometers per second, carrying music and heartbeats and greetings in 55 languages through the dark between the stars. Let us now talk about the specific people working on Voyager today, about what it is like to be part of a team maintaining a 47-year-old spacecraft in interstellar space. The Voyager team at JPL is small by the standards of major NASA missions. A few dozen engineers, scientists, and operations personnel. Some have been on the project for decades. Some joined recently and are learning the specific character of a spacecraft whose design predates personal computers. The team has a particular relationship with time. When you work on Voyager, you are constantly working in multiple time frames simultaneously. There is the time frame of the mission, the 47-year history that defines what Voyager is, what it has been through, what decisions were made, and why. There is the time frame of current operations, the daily work of scheduling communication sessions, receiving and processing telemetry, analyzing what the instruments are seeing right now. And there is the time frame of the future, the calculations of how much longer each system can operate, the planning of which instruments to shut down when, the preparation for the eventual end. Most of the people currently working on Voyager were not alive when it was launched. They inherited a spacecraft they did not build, running software they did not write, with documentation about systems whose designers are mostly no longer available to consult. To work on Voyager in 2024 is to take custody of something created by people you never met, in a world you did not inhabit, using technology that has been obsolete for decades, and to keep it alive. The November 2023 memory failure tested this custody in the most acute way possible. For several months, Voyager 1 was transmitting but not communicating, sending a carrier signal and corrupted data rather than readable telemetry. The team did not know the state of the spacecraft. Every attempt to diagnose required 44 hours of waiting. Every hypothesis about what had failed required a test that itself took 44 hours to evaluate. The engineers who solved this problem did so by reading documentation from 1977, by consulting retired colleagues who remembered decisions made half a century ago, and by reasoning carefully about a computer system they had never built and could not directly inspect. They solved it from 23 billion kilometers away, through a communication link slower than a 1970s telegraph, with a 44-hour turnaround on every action. When full communication was restored in April 2024, the emotion in the Voyager operations area at JPL was real. Not performance, not ceremony. Real relief and real joy from people who had spent months worrying about something they cared about deeply. Voyager 1 is a machine. It does not know it was almost lost. It does not know it was recovered. But the people who kept it alive know both of these things. And the knowledge that a 47-year-old spacecraft in interstellar space can still be saved by a small team of dedicated engineers working across a 44-hour communication gap, that knowledge matters. It matters for what we understand about human capability and human commitment. Let us now talk about the night-sky connection, about what you can do right now to make the abstract fact of Voyager 1's location into something concrete and personal. Voyager 1 is moving in the direction of the constellation Ophiuchus, roughly between Ophiuchus and the direction away from the galactic centre. On the celestial sphere, this corresponds to approximately right ascension 17 hours 13 minutes, declination plus 12 degrees. This region of sky is visible from most of Earth in summer evenings in the northern hemisphere. Ophiuchus rises in the south, lower toward the horizon. In the southern hemisphere, it is higher and more prominent. Tonight, if the sky is clear, go outside and find this region. You will not see Voyager. No telescope accessible to you would show it. It is far too small and reflects insufficient light. But you can look in the direction of Ophiuchus, knowing that there, on the far side of all those stars, beyond the constellations you can name, in interstellar space, on a trajectory passing through that region of the sky, Voyager 1 is right now travelling. The stars you see in that direction are hundreds to thousands of light years away. Voyager is about 22 light hours away, thousands of times closer than the nearest visible star in that direction. But it is in the same direction. That direction on the sky is where the most distant human-made object is. This exercise, finding the direction on an actual sky above your actual head, transforms the abstract into something spatial. It gives Voyager a location that is real to your senses, rather than just a number. The direction is there. The spacecraft is there. The golden record is there. Every hour you spend looking at that part of the sky, Voyager moves approximately 61,000 kilometers farther in that direction. Let us now talk about one more specific aspect of Voyager's story that is rarely discussed, but that is central to understanding what the mission means, about the role of uncertainty in long-duration space exploration. When Voyager 1 was launched in 1977, the team knew what it would encounter at Jupiter, within the limits of what the Pioneer 10 and 11 spacecraft had measured during earlier flybys. They knew less about Saturn. They knew almost nothing about the specific character of the heliopause, whether it would be a sharp boundary or a gradual transition, where exactly it would be, what they would find on the other side. Every phase of Voyager's journey has involved entering conditions that had never been directly measured before. The instruments were designed to measure whatever they encountered, not calibrated for a specific known environment. This is different from many modern space missions, which are designed to measure specific quantities in environments that are much better characterized from previous observations. Voyager's instruments encountered genuine surprises. The magnetic field geometry at the heliopause was not as expected. The plasma density in interstellar space was higher than some models predicted. The transition zone between heliosphere and interstellar space, the heliosheath, turned out to be more complex and structured than simple models suggested. These surprises are valuable precisely because they are surprises. They tell us that our models were wrong in specific ways. And being wrong in specific ways, rather than generally uncertain, is how science makes progress. Voyager 1 gave us specific wrongnesses to correct. The next generation of measurements, from whatever interstellar precursor missions follow Voyager, will go in knowing what Voyager found. They will be able to design instruments and trajectories specifically to address the questions Voyager's surprises raised. This is the cumulative nature of scientific exploration. Each mission defines what the next one should ask. Let us now talk about something that connects all of these threads, about what Voyager 1 reveals when you look at it not as a spacecraft, but as a human artifact. Every civilization that has ever existed on Earth has left physical artifacts. Some of them have survived thousands of years. The pyramids, the Parthenon, the Great Wall, the cave paintings of Lascaux. Some of these artifacts will survive for thousands more years if civilization continues to maintain and protect them. None of them will survive billions of years. Erosion, weathering, biological decomposition, plate tectonics, these processes operate on geological timescales and will eventually return everything built on Earth's surface to undifferentiated rock or sediment. Voyager 1 is exempt from these processes. In the vacuum of interstellar space, there is no erosion in the terrestrial sense, no moisture, no biological activity, no plate tectonics. The spacecraft will be degraded very slowly by the cumulative effect of interstellar dust impacts and high-energy particle bombardment from cosmic rays. But these processes operate on timescales that make the most durable Earth surface artifact look ephemeral. The golden record, a gold-plated copper disc in an aluminium case, will remain structurally intact and informationally readable for an estimated billion years or more under interstellar space conditions. This means Voyager 1 is, by a very large margin, the most durable physical artifact of human civilization ever created. The pyramids of Giza, estimated to survive in recognizable form for perhaps another few tens of thousands of years before erosion renders them unrecognizable hills. The golden record, estimated to survive in readable form for another billion years. The ratio is roughly 100,000 to 1. This is not a coincidence of engineering, it is a consequence of environment. Earth's surface is hostile to physical preservation on geological timescales. Space is not. Moving something into interstellar space is the most effective preservation strategy available to us. This raises a strange thought. If Voyager 1's golden record is the most durable artifact of human civilization, then the image of humanity carried into the deepest future is not the Mona Lisa, not Shakespeare, not the works of any architect or composer or scientist. It is 90 minutes of music selected by a group of people in 1977, 116 photographs chosen to represent Earth, greetings in 55 languages, and the brainwaves of Anne Druyan thinking about love and the history of the world. That is what will last. That specific selection made by those specific people in that specific year. There is something both arbitrary and profound about this. Arbitrary because the selection was made with urgency and with real constraints of time and format. Profound because the selection, for all its limitations, genuinely tried to represent the breadth of human experience rather than the narrowness of any particular tradition. Whether it succeeds in this representation depends on a listener who may never exist, but the attempt is there. Flying through interstellar space, longer lasting than anything else we have made. Let us now talk about the mathematical reality of Voyager's journey in a way that makes the scale visceral rather than abstract. Light travels at about 300,000 kilometers per second. In 1 second, light travels from here to the Moon and back several times. In 8 minutes, light travels from the Sun to Earth. Voyager 1 is at a distance that light takes more than 22 hours to cross. Not 22 minutes, 22 hours. If you drove a car at highway speed, 100 kilometers per hour, continuously without stopping, How long would it take to reach Voyager 1's current distance? 23.5 billion kilometers at 100 kilometers per hour, 235 million hours, about 26,800 years. If you could somehow fly to Voyager on a commercial aircraft at 900 kilometers per hour, about 3,000 years. If you travelled on the fastest crewed spacecraft ever launched, Apollo 10, which reached about 39,897 kilometers per hour during Earth re-entry, about 660 years. On Voyager 1 itself, travelling at 17 kilometers per second, 61,200 kilometers per hour, about 383 years to cover its own current distance from the Sun. None of these comparisons convey the distance intuitively. That is because human intuition has no framework for distances of this magnitude. We evolved to navigate landscapes measured in kilometers, not billions of kilometers. The human brain has no direct sensory experience of the scale at which interstellar distances operate. This is one of the reasons the night sky is misleading. The stars appear close. They are pinpoints of light that seem no farther away than the lights of a distant city. They are hundreds of thousands of times farther than the most distant visible landscape feature on Earth. Voyager 1 is somewhere between, closer than the nearest star by a factor of thousands, but so far that light takes most of a day to cross the gap. The number 23.5 billion kilometers feels like a large number. It is, but within the galaxy, it is almost nothing, less than 1/1,000,000th of the galactic diameter. This is the context in which Voyager 1 travels. Astonishingly far by human standards, vanishingly local by cosmic standards. Let us now talk about the relationship between Voyager 1 and time, about what 47 years of continuous operation means in terms of human history and institutional continuity. The Voyager project began in the early 1970s, the world of 1972 when serious planning began. The Vietnam War was still ongoing. The Apollo program was ending. The last moon landing, Apollo 17, was in December 1972. The Cold War was at a particular inflection point. Détente, SALT negotiations, Nixon in China. None of the current generation of Voyager engineers had been born. In 1977, when Voyager launched, the first personal computers were just appearing. The first Star Wars film was released the same summer. Disco was at its peak. The Soviet Union appeared to be a permanent fixture of geopolitics, with no sign of the changes that would come 12 years later. In 1990, when the pale blue dot was taken, the Berlin Wall had fallen the previous year. The Cold War was effectively over. The internet existed, but was not yet a public network. In 2012, when Voyager crossed the heliopause, smartphones were ubiquitous, social media was dominant. The scientific community had been transformed by computational tools that the Voyager team of 1977 could not have imagined. In 2024, as Voyager continues, artificial intelligence is reshaping science and engineering. Space exploration has diversified to include commercial entities alongside national agencies, and the Voyager team maintains a 1970s-era spacecraft using documentation that predates many of their own careers. Through all of this, through political upheaval, through technological revolutions, through the deaths of its creators and the births of its current custodians, Voyager 1 has been doing exactly what it was programmed to do: moving forward, measuring, reporting. Its continuity through all this human change gives it a kind of stability that human institutions rarely achieve. Governments change, companies rise and fall, ideologies come and go. Voyager 1 just keeps flying. There is something grounding about this. In a world of rapid change and constant disruption, a 47-year-old spacecraft in interstellar space, still transmitting, still measuring, still going, represents a kind of reliable continuity, not of people or institutions, but of the physics that governs its motion and the mathematics that describes its trajectory. The same equations that Jerry Flandreau used to calculate the Grand Tour trajectory in 1972, Newton's law of gravitation, the conservation of angular momentum, still accurately predict where Voyager 1 is today, to within a tiny fraction of a percent. No revision needed, no update required. The physics was right in 1972 and is still right in 2024. That reliability of the physical laws that govern Voyager's motion through space is perhaps the most durable thing about the mission. Not the spacecraft itself, which will eventually fall silent. Not the golden record, which will last 1 billion years, but not forever. The mathematical description of the trajectory will remain valid as long as general relativity remains our best theory of gravitation. Voyager 1 moves through space according to equations that will outlast it, that were written before it was launched, and that will remain valid long after the civilization that wrote them has changed beyond recognition or ceased to exist. This is what physics is. Not a human invention, but a description of how the universe already works. Voyager moves through interstellar space the way it moves because the universe was already organized to produce exactly this behavior. The equations describe that organization. The spacecraft reveals it. Let us now talk about one more specific thing before we approach the end of tonight's journey, about what the experience of tracking Voyager in real time can feel like. There is a website, voyager.jpl.nasa.gov, where the current distance and speed of both Voyager 1 and Voyager 2 are displayed in real time. The numbers update continuously. Distance in kilometers and in astronomical units. Speed in kilometers per hour. One-way light time in hours and minutes. If you look at this page right now, the number showing Voyager 1's distance from the Sun is slightly different from what it was an hour ago. In 1 hour, Voyager travels about 61,200 kilometers. The number is always increasing. It has been increasing every second for 47 years. This live updating number is one of the few ways to make the abstract into something experiential. It is not a historical record. It is not an archived value. It is the current distance to the most distant human-made object, updating in real time, reflecting exactly where Voyager is right now. Look at the light time figure. That number, currently more than 22 hours, tells you how long the most recent signal from Voyager took to reach Earth. It also tells you that, right now, at this moment, a new signal is travelling from Voyager toward the antennas of the Deep Space Network. Launched at the speed of light from a 23-watt transmitter, heading toward a 70-metre dish in Goldstone or Madrid or Canberra. That signal is in transit right now. You cannot detect it, cannot see it, cannot intercept it, but it is real, it exists. Moving at 300,000 kilometers per second through interstellar space and then through the heliosphere and toward Earth. In 22 hours it will arrive. This is happening right now as you read this. Let us talk about something that deepens our understanding of Voyager 1's journey, about what the spacecraft has taught us about the concept of a boundary and why boundaries in nature are more complex than we imagine. When Voyager 1 was launched, the heliopause was a theoretical construct. Scientists knew the solar wind existed. The first direct measurements of the solar wind were made in the early 1960s by the Mariner 2 spacecraft on its way to Venus. They knew the solar wind must eventually encounter resistance from the interstellar medium. The boundary where this happened was called the heliopause, but no one had ever been there. No one knew what it looked like. The standard model predicted a relatively sharp transition: the solar wind on one side, interstellar medium on the other, boundary in between. Clean, definite, like a line on a map. What Voyager found was more complex. The approach to the heliopause, a region called the heliosheath, the zone between the termination shock and the heliopause itself, took years to traverse. During this traversal, the instruments detected a region that was neither clearly heliospheric nor clearly interstellar. The magnetic field fluctuated. The particle fluxes varied on timescales of days. There were episodes where conditions seemed to suggest Voyager had crossed into interstellar space, then receded back into heliospheric conditions. This oscillating behavior near the boundary was not predicted by simple models. It suggests the heliopause is not a fixed surface, but a dynamic one, moving in and out as the solar wind pressure varies with the solar cycle, and as the pressure of the interstellar medium varies with the local structure of the interstellar gas cloud through which the heliosphere is moving. The heliopause breathes. It is not a wall. It is a fluctuating interface between two dynamic fluid systems, the solar wind and the interstellar medium, each pushing against the other, with the boundary position determined at every moment by the instantaneous balance of pressures on both sides. This is a general lesson about boundaries in nature that Voyager illustrated at cosmic scale. The edge of the ocean on a beach is not a line, it is a zone that moves with every wave, with every tide, with every storm. The edge of a forest is not a line, it is a gradual transition zone where forest species thin out and meadow species appear. The edge of a city is not a line, it is a zone of mixed urban and rural character. Nature rarely draws sharp lines. It usually creates transition zones. The heliopause is the transition zone between the heliosphere and interstellar space. It has a width. It fluctuates. It is real, but it is not sharp. Understanding this has practical implications for planning future interstellar missions. A spacecraft designed to operate in the heliosheath will encounter conditions different from those both inside the heliopause and outside it. The instruments need to be designed for this complex transition zone. The trajectory needs to account for the fact that the boundary location is not fixed. Voyager 1 gave us our first direct measurements of this transition zone. The picture it provided is more nuanced than the simple boundary we imagined before it arrived. Let us now talk about the specific role of Jupiter in Voyager's story. Not just as a source of gravitational acceleration, but as a site of major discovery that transformed planetary science. When Voyager 1 arrived at Jupiter in March 1979, the mission was already a scientific mission rather than simply a transit. Jupiter was not just a slingshot for Voyager, it was a destination in its own right. The discoveries at Jupiter were extraordinary. Io, the innermost of the 4 large Galilean moons, was found to have active volcanoes. The discovery was made by navigation engineer Linda Morabito, who was examining an image of Io to check the position of a background star for navigation purposes. She noticed an umbrella-shaped plume rising from Io's surface, volcanic material being ejected into space. This was the first observation of active volcanism beyond Earth. It transformed our understanding of what kinds of worlds could be geologically active. Before Voyager, The assumption was that a moon-sized body would be geologically dead, too small to retain heat for billions of years. Io proved this assumption wrong. Tidal heating from Jupiter's powerful gravity keeps Io's interior molten, even though the Moon is small and old. The discovery of Io's volcanoes also opened a new question. If Io is heated by Jupiter's tides, what about Europa? Europa, the next moon out from Io, also experiences tidal forces. The images Voyager returned of Europa showed a smooth surface crossed by dark lines, a surface that looked like nothing so much as cracked ice floating on a liquid beneath. The implication was immediate. Europa might have a subsurface ocean, kept liquid by tidal heating. This was not confirmed during the Voyager flyby. The resolution was insufficient, and the mission was not designed to investigate this specific question. But the idea took hold in the scientific community and has been pursued ever since. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, gathered strong evidence for the subsurface ocean. NASA's Europa Clipper mission, launched in October 2024, is specifically designed to characterize this ocean and assess Europa's potential habitability. The chain runs directly from Voyager's 1979 images of a cracked, icy surface to the Europa Clipper spacecraft now in transit toward Jupiter. One image of a strange surface, one implication recognized by scientists looking at the data, set in motion a scientific pursuit that is still unfolding 45 years later. This is how science accumulates. An image raises a question. The question motivates a hypothesis. The hypothesis demands a test. The test requires a mission. The mission takes decades to plan, fund, build, and launch. The answer arrives decades after the original question was raised. The patience this requires is not merely scientific virtue, it is an operational necessity. The universe does not accommodate itself to human impatience. The timescales on which planets and moons evolve, on which spacecraft traverse interplanetary distances, on which scientific programs bear fruit, these timescales are geological and astronomical, not human. Voyager illustrated this at the outset. It took 8.5 years from launch to reach Uranus. The results from the outer planets took years to analyze fully. The crossing of the heliopause took 35 years after launch. The memory recovery in 2024 took several months of careful diagnostic work across a 44-hour communication gap. None of this fits within a news cycle, or a grant period, or an electoral cycle. It requires institutions with longer time horizons than most human enterprises. NASA's maintenance of the Voyager program through budget cycles, through administration changes, through the shifting priorities of half a century of American politics, this institutional continuity is itself a remarkable achievement. Let us now talk about something that is simultaneously technical and deeply human, about the specific experience of the engineers who send commands to Voyager 1, and what the 44-hour wait between command and response feels like in practice. Imagine you are a Voyager flight engineer at JPL. You have identified an anomaly in the telemetry. A reading from one of the instruments is slightly off from expected values. You need to diagnose whether this is a real instrumental issue or a telemetry artifact. You write a diagnostic command. You review it with your team. You check it against the documentation from the 1970s. You verify it against simulations. You send it. Then you wait. The command is traveling through space at the speed of light. It will take 22 hours and some minutes to reach Voyager. You know the exact moment it will arrive. The navigation team can calculate this to the minute based on Voyager's precisely known position and velocity. At that moment, Voyager's computer will execute the command. The response will begin travelling back. Another 22 hours. While you wait, you go home. You sleep. You come back. You work on other things. You have lunch. You go home again. You sleep again. You come back the next day. And then the response arrives. This is the rhythm of working with Voyager. Every interaction is a 2-day event. No immediate feedback. No real-time troubleshooting in the ordinary sense. You form a hypothesis, you test it, and you wait 2 days to know if you were right. If you were wrong, you form a revised hypothesis, send another command, and wait another 2 days. During the November 2023 memory failure, this process played out over months. Dozens of command response cycles, each taking 2 days, gradually narrowing the diagnosis from "we do not know what is wrong" to "we know exactly which memory locations are damaged and what code needs to be moved." The engineers who did this work describe it as requiring a particular kind of patience that is different from ordinary engineering problem solving. On a normal engineering project, you can iterate quickly. Try something, see the result immediately, try something else. With Voyager, the iteration time is measured in days. The feedback loop is slow. You have to be right more often, have to think more carefully before sending each command, because each wrong guess costs 2 days rather than 2 seconds. And you have to maintain engagement over months of this slow process. The memory recovery did not happen in a single brilliant insight. It happened through sustained methodical work over many months of 2-day iteration cycles. The engineers who maintained that engagement, who kept returning to the problem day after day and week after week, deserve credit not just for technical skill, but for a particular kind of commitment. Let us now talk about the future of Voyager's data, about what happens to the scientific record after the mission ends. The data from Voyager 1, 47 years of telemetry from instruments ranging from the outer planets to interstellar space, is archived in multiple formats at multiple institutions. The primary archive is the NASA Space Physics Data Facility. Secondary archives exist at JPL and at the National Space Science Data Center. The earliest Voyager data, from the late 1970s and early 1980s, was originally recorded on magnetic tape in formats specific to the computing systems of that era. Some of this data has been re-archived in modern formats as part of data preservation efforts. Some may still require legacy software or hardware to read in original form. This is not a problem unique to Voyager. Every long-running scientific program faces the challenge of data format obsolescence. The solution, ongoing migration of data to current formats, maintenance of format conversion tools, documentation of original formats, is effort-intensive but necessary. Scientists using Voyager data today are often doing things that were not possible when the data was collected. The magnetometer measurements from the heliosheath region, for example, can now be analysed with models of the heliospheric magnetic field that are far more sophisticated than those available in the 2000s. Reanalysis of this data with modern tools has produced new insights that were not extracted from the original data at the time of collection. This will continue after the mission ends. The data collected in Voyager's final years, measurements of interstellar space at its farthest extent, the last readings from each instrument before shutdown, will be available to scientists for decades. New analytical techniques, new theoretical frameworks, new questions motivated by future discoveries, all of these will find applications in the Voyager archive. The scientific life of Voyager does not end when the last signal arrives. The archived data will outlive the mission by decades or centuries. Future scientists will mine it for insights that we cannot currently anticipate. This is the long tail of scientific missions. The way data collected at one moment in history continues to yield insights long after the moment of collection. Voyager's archive is part of this long tail. The first full scientific exploitation of the interstellar space data may still lie ahead of us, waiting for the right questions and the right analytical tools. Let us now talk about what Voyager 1 means for one of the deepest questions in human thought, about whether we are alone. The Golden Record was created with the explicit understanding that if there is other intelligence in the universe, communication with it would be worth attempting. Carl Sagan spent much of his career thinking about this question, about whether the universe contains other minds, about what we could say to them, about how we might recognize them. Voyager's Golden Record is a practical attempt to act on this question. Not to wait until we are certain intelligence exists elsewhere, not to wait until we know how to contact it efficiently, but to do something now, with what we have, at the opportunity that presents itself. The probability that the record will be found is vanishingly small. Sagan knew this. He created it anyway. The act was not about probability, it was about intention. About what kind of civilization we choose to be when we have the option to reach out into the cosmos. A civilization that, when it has its first opportunity to send something beyond the solar system, chooses to include music and heartbeats and greetings. That civilization is expressing something about its values. It is saying that the possibility of connection, however remote, is worth attempting. That beauty and culture and the diversity of human expression are things worth sharing with whatever might be listening. This intention to reach out, to share, to attempt connection is not naive. It coexists with a clear-eyed understanding of the distances and the probabilities involved. It is not optimism about contact happening, it is commitment to trying, regardless of whether it happens. This is one of the most admirable things about the Voyager mission. In 1977, people who understood the physics of interstellar distances and the vanishingly small probability of the record ever being found chose to include it anyway. Not from ignorance of the odds, from a decision that the attempt was worth making. 50 years from now, or 1,000 years from now, or 1 billion years from now, if the Golden Record is ever found, and its music is played for the first time to ears that did not evolve on Earth, that moment will be the fulfillment of an intention formed by humans in 1977, embedded in a copper disc and sent into the dark. The record is a bet on the future, a very long bet with very long odds, but a bet made seriously and with full understanding of what it means to make it. Let us now talk about the specific present moment, about what Voyager 1 is doing right now, today, in a way that makes tonight's sky meaningful. Right now, as you read this, Voyager 1's 4 remaining scientific instruments are taking measurements. The magnetometer is measuring the direction and intensity of the interstellar magnetic field at Voyager's current position. This field is part of the galaxy's large-scale magnetic structure, the field that pervades the spiral arms of the Milky Way and influences how cosmic rays travel through the galaxy. No other instrument has ever measured this field from inside the local interstellar medium. The plasma wave system is listening for low-frequency electromagnetic oscillations in the surrounding plasma. If the Sun produces a significant coronal mass ejection in the coming months, a wave of disturbance will eventually reach Voyager, and the plasma wave system will detect it, measuring the interstellar plasma's response to this disturbance and allowing calculation of the plasma density at Voyager's location. The low-energy charged particle detector is counting particles, measuring the energy spectrum of the ions and electrons in Voyager's immediate environment. The galactic cosmic rays, arriving from all directions, carry information about their sources: supernova remnants, pulsars, active galactic nuclei, and their energy spectrum encodes information about how they have travelled through the interstellar medium to reach Voyager's detector. The cosmic ray detector is measuring higher energy particles, galactic cosmic rays of greater energy that penetrate deeper into matter, and that came from more energetic sources or travelled for longer times or across greater distances. All of this data is being recorded, formatted by the onboard FDS computer, the same computer whose memory was damaged by a cosmic ray in 2023 and repaired through months of careful work by the JPL team, queued for transmission during the next communication session. Then the signal goes out, 23 watts of radio energy at 8.4 gigahertz, aimed at Earth at a target that is not a point but a moving one, a planet rotating and orbiting the Sun, its position 22 hours in the future, calculated to arc-second precision by the navigation team. The signal travels. It crosses the heliosheath. It crosses the heliopause, the boundary that Voyager itself crossed in 2012. It enters the heliosphere, the Sun's domain. It travels inward, past the outer planets, past the asteroid belt, through the inner solar system. It arrives at Earth, specifically at whatever DSN antenna is currently pointed at that region of sky. The antenna receives it. At a power level of about 2 times 10 to the minus 20 watts, after 22 hours of travel at the speed of light. And the data is read, decoded, calibrated, archived, analysed. The most distant signal in human history received right now, today. Look in the direction of Ophiuchus tonight. That is where it is coming from. Let us talk about something that has not come up yet, about the specific relationship between Voyager 1 and the Sun, and about what the Sun looks like from interstellar space. From Voyager 1's current distance of 157 astronomical units, the Sun is still the brightest object in the sky, but it no longer looks like a sun in the familiar sense. At 157 times the Earth-Sun distance, the Sun's apparent brightness falls by the square of the distance. 157 squared equals about 24,600 times fainter than it appears from Earth. The Sun seen from Earth has an apparent magnitude of about minus 26.7. From Voyager 1's distance, it would appear at about magnitude minus 16. This is still extraordinarily bright. About 6 magnitudes fainter than from Earth means 250 times fainter. The Sun from Voyager 1 is still roughly 100,000 times brighter than the full Moon as seen from Earth. So, from Voyager's perspective, the Sun is a dazzling star, not the disk we know, but a point source of overwhelming brilliance. Still bright enough to be dangerous to look at directly without shielding. Still bright enough to cast faint shadows on the spacecraft's surface, but dim enough that the solar system around it is invisible. The planets, Earth, Mars, Jupiter, are hundreds or thousands of times fainter than they would need to be to detect without a telescope. From 157 astronomical units, Earth's maximum brightness is roughly magnitude 4, barely visible to the naked eye if you knew exactly where to look against the glare of the nearby Sun. The Sun's angular diameter from Voyager's distance, about 0.001 degrees, or 3.6 arcseconds, too small to resolve as a disk even with a small telescope. From this distance, the Sun would appear as a point, an overwhelming point, but a point. This is the perspective from which Voyager sees the solar system it was built in. The system that contains Earth, contains JPL, contains the people who built it, compressed into a region of sky a few arcseconds across, dominated by a star that is the overwhelmingly brightest thing in view, but still recognizably just a star. This perspective, the view from outside, is what the pale blue dot photograph attempted to capture, though imperfectly because the cameras were pointed at the solar system from 40 astronomical units rather than 157. At 157 astronomical units, the entire solar system, including all planets, fits within an angular region about the size of a large lunar crater, as seen from Earth. The solar system from interstellar space is tiny. This is not a metaphor or a philosophical point. It is a literal geometric fact. Everything we have been, everything we have done, every spacecraft we have ever launched, every radio signal we have ever transmitted, all of it originates from a region of sky that Voyager could cover with its thumbnail, if it had a thumb. Let us now talk about the specific scientific question that has been most transformed by Voyager's interstellar measurements, about the nature of the local interstellar medium, and how Voyager's data fits into the broader picture of our stellar neighborhood. The Sun is currently moving through a region of space called the local interstellar cloud, sometimes called the local fluff. This is a warm, partially ionized cloud of gas about 30 light-years across. The Sun entered this cloud within the past 100,000 years or so. Before that, it was traveling through a slightly different medium. Voyager's measurements of the interstellar magnetic field, plasma density, and particle fluxes are all measurements of the local interstellar cloud. The physical conditions Voyager detects, temperature, density, ionization state, magnetic field strength, all characterize this specific cloud rather than interstellar space in general. The local interstellar cloud is itself embedded in the local bubble, the larger region of hot, rarefied plasma we mentioned earlier. The cloud is a cooler, denser inclusion within this hot bubble, like a cloud within a larger atmosphere. This context matters for interpreting Voyager's data. The interstellar medium Voyager is measuring is not a generic sample of galactic interstellar medium. It is a specific sample of one specific cloud in one specific bubble at one specific location in the galaxy. Different locations in the galaxy would have different conditions. Future interstellar missions, traveling in different directions or to greater distances, would sample different interstellar conditions and would allow comparison. Building up a picture of how interstellar conditions vary across the local galactic neighborhood requires multiple data points. Voyager provides one. The proposed interstellar probe would provide a second. Eventually, a network of interstellar measurements might map the local interstellar medium in 3 dimensions. We are not close to this goal. Voyager gives us one data point in one direction at one distance. It is the most important data point we have, but it is one. Let us now talk about the question of what Voyager's data tells us about the safety of interstellar travel for future human missions to other stars, if such missions ever become possible. One of the most important practical questions for interstellar flight is the radiation environment. A crewed spacecraft traveling from the solar system to another star would spend years in interstellar space. The crew would be exposed to galactic cosmic rays throughout this time, without the partial protection that the heliosphere provides within the solar system. Voyager's cosmic ray measurements beyond the heliopause give us the most direct available measurement of this radiation environment. The galactic cosmic ray flux in the local interstellar medium, as measured by Voyager, is about 30 to 40% higher than inside the termination shock, and significantly higher than at Earth's orbit. This is the baseline radiation environment for interstellar travel. For a human crew on a hypothetical interstellar mission, the dose from galactic cosmic rays alone would accumulate at a rate of several hundred millisieverts per year in the local interstellar medium, assuming no additional shielding beyond a spacecraft structure similar to current crewed spacecraft. For a 10-year transit to Alpha Centauri, achievable only with propulsion systems far beyond current technology, this would mean an accumulated dose of several sieverts from galactic cosmic rays alone, exceeding current lifetime limits for space workers. This means that interstellar crewed missions, in addition to solving the propulsion problem, would also need to solve the radiation problem. Heavy shielding adds mass. More mass means more propulsion required. This engineering interaction makes the problem harder rather than easier. Voyager's measurements quantify exactly how hard. The dose rate it measured in interstellar space tells us what any future crewed interstellar ship would face. That is actionable information, even though the technology to act on it is centuries away. Let us now talk about something that is both concrete and moving, about what will happen on the day the last Voyager signal arrives at Earth. That day is coming. The engineers know it is coming. The instruments are running down. The power is decreasing. At some point in the late 2020s, perhaps 2028, perhaps 2029, the exact date depends on how the aging RTGs perform in their final years. The last scientific data will be transmitted. The team will know in advance approximately when this will happen. As each instrument is shut down one by one to conserve power, the team will be counting down toward the final shutdown. There will be planning discussions about which instrument should be last, which measurement is most valuable to preserve to the very end. The final instrument shutdown will be commanded deliberately. A command will be sent from JPL, traveling 22 hours to reach Voyager. Voyager's computer will execute the command. The last scientific instrument will power down. The last scientific data will have already been transmitted. What remains after that, for some period, will be a carrier signal, Voyager transmitting radio waves without any data modulated onto them. Just the presence signal. I am here. I am alive. The transmitter is on. This carrier will persist until the RTG power falls below the level needed to maintain even the transmitter. Then, silence. The DSN antenna receiving that carrier signal will notice when it stops, perhaps abruptly if a power threshold is crossed, perhaps gradually if the signal fades. The navigation team will verify that the silence is real, not a temporary interruption. The mission status will be updated. The mission will be declared complete. Not failed, complete. Voyager 1 will have done everything it was asked to do, and everything it was not asked to do. It will have exceeded every expectation by decades. It will have been the first human-made object to visit Jupiter up close, to send back images of Io's volcanoes and Europa's cracked ice, to fly past Saturn and Titan, to leave the solar system, to transmit data from interstellar space for more than a decade. It will have done all of this and then gone silent. The silence will not be the end of the story. The spacecraft will continue. The golden record will continue. The trajectory through interstellar space will continue, calculated by the same equations that have accurately described it for 47 years in the absence of any transmitters or receivers to verify it. The silence will simply mark the end of the conversation, and it will be a conversation worth having had. Let us now talk about what the total legacy of Voyager 1 looks like when you try to list it, because a partial inventory makes clear how much was accomplished by this one spacecraft. Scientific discoveries. First, close images of Jupiter's great red spot, in detail sufficient to see its internal structure. Discovery of active volcanism on Io, the first beyond Earth. First, detailed images of Europa, suggesting a subsurface ocean. Discovery of Jupiter's ring system, thin and dusty, unlike Saturn's. Discovery of 3 of Jupiter's smaller moons. First detailed images of Saturn's rings, revealing their complex, fine structure. Discovery that Saturn's rings are accompanied by thousands of smaller ringlets, separated by gaps. Detailed images and atmospheric measurements of Titan, revealing a dense nitrogen-methane atmosphere. First close images of 5 Saturn moons. Discovery of several additional Saturn moons. Measurement of Saturn's rotation period more accurately than previously known. First direct measurement of the solar wind termination shock. First direct measurement of the heliosheath properties. First crossing of the heliopause and first measurements in interstellar space. First direct measurement of interstellar plasma density. First direct measurement of the interstellar magnetic field in the local interstellar medium. First measurement of the galactic cosmic ray flux, unmodulated by the heliosphere. Cultural and philosophical contributions. The pale blue dot photograph, one of the most widely reproduced and discussed scientific images in history. The golden record, the most durable artifact of human civilization. Voyager's 40-year trajectory calculations, demonstrating the extraordinary precision of Newtonian mechanics and celestial navigation. The demonstration that spacecraft can operate for half a century with nuclear power sources and survive the transition from planetary space to interstellar space. Institutional and technical contributions. Development and demonstration of gravitational assist trajectories that have been used by virtually every subsequent outer planet mission. Development of deep space communication techniques, enabling reception of signals at power levels of 10 to the minus 20 watts. Demonstration of long-duration spacecraft operation, including management of aging RTGs and maintenance of attitude control over decades. This list is not complete. Every item on it has spawned follow-on research, follow-on missions, and scientific papers that fill libraries. The downstream scientific impact of Voyager 1's discoveries is incalculable, but the list gives a sense of scale. 1 spacecraft, 47 years, this much. Let us now talk about something specific that you can do tonight that connects you directly to the story of Voyager 1. Something beyond simply looking in the direction of Ophiuchus. Go to the NASA website or to voyager.jpl.nasa.gov and look up Voyager 1's current distance. Write down the number, the exact distance in kilometers or in astronomical units. Then look at that number again tomorrow. Note how much larger it is. The difference, about 1.5 million kilometers in 24 hours, is the distance Voyager travels every day. This daily increment is the most concrete way to feel the passage of time in the context of Voyager's mission. 1.5 million kilometers per day. 61,200 kilometers per hour. 17 kilometers per second. At this rate, in the year since you first looked at this page, Voyager has travelled about 540 million kilometers farther, more than 3 times the Earth-Sun distance, in 1 year. And yet, the nearest star is still 4.37 light-years away, about 41 trillion kilometers. At Voyager's current speed, 73,000 years to reach it, if it were heading there, which it is not. The numbers are irreconcilable in a human intuitive sense. They simply are what they are. The speed is genuinely enormous by human standards. The distances are genuinely incomprehensible by human standards. Both things are true simultaneously. The exercise of tracking the daily increment, watching the number change, makes both of these things feel real in a way that simply reading about them does not. Voyager is genuinely moving that fast. The distance is genuinely that large. And right now, as you read this, both things are true at once. The spacecraft is moving at 17 kilometers per second through interstellar space. The nearest star is 73,000 years away at that speed. Both true, simultaneously, right now. Let us now talk about the simple fact of duration, about what 47 years of continuous operation means in comparison to other things that have lasted that long. 47 years ago, September 1977, the same year, Elvis Presley died. The first Star Wars film was in theaters. The Apple II personal computer was introduced. Disco was at its peak. Jimmy Carter had been President of the United States for 8 months. People who were born the year Voyager launched are now in their late 40s. People who were adults when it launched are now elderly. Many of the engineers who designed and built it have died. Countries that existed when Voyager launched no longer exist. The Soviet Union, which was Voyager's competitor in the space race at the time of its launch, dissolved 14 years later. Yugoslavia no longer exists. Rhodesia became Zimbabwe. West and East Germany reunified. Technologies that did not exist when Voyager launched are now obsolete. The first cell phones appeared in the early 1980s, after Voyager launched, and those early cell phones are now museum pieces. The Internet became publicly available in 1993, 16 years after Voyager launched. Smartphones appeared in 2007, 30 years after Voyager launched. Technology has gone through several complete generational turnovers. Through all of this, Voyager 1 has been flying, measuring, reporting. The continuity of the mission across half a century of human change is one of its most remarkable aspects. Not the speed, not the distance, not even the discoveries, but the simple, stubborn fact of continuing to function through everything that has changed on Earth since 1977. This continuity is not accidental. It required sustained institutional support through multiple administrations, through budget cycles, through the competing demands of new missions and new priorities. The people at JPL who kept Voyager funded and operational through all of this deserve credit that is rarely given. The credit not for the dramatic moments of discovery, but for the unglamorous work of maintaining something over decades. Discovery is celebrated. Maintenance is invisible. But without maintenance, discovery stops. The discoveries of 2012 and beyond exist because people maintained Voyager through the quiet years between planetary flybys. The people who kept the lights on deserve as much recognition as those who were present for the photogenic moments. Let us now talk about one final specific thing, about the relationship between Voyager 1 and the concept of legacy. We talk about human legacy in many contexts: the buildings people leave behind, the books they write, the children they raise, the institutions they found, the scientific discoveries they make. All of these are forms of legacy, ways in which the effects of a life persist after the life ends. Voyager 1 is a specific and unusual form of legacy. It is not a legacy of words or buildings or institutions, all of which are fragile in their own ways. It is a physical legacy in the most literal sense, a physical object moving through physical space, carrying physical information. The engineers and scientists who created Voyager in the early 1970s, many of whom are now dead, are represented in interstellar space by the specific decisions they made. The choice of which instruments to include, the choice of the trajectory that used Jupiter's gravity to reach Saturn, the choice of which scientific questions to prioritize, the design of the RTGs with power margins that have enabled 47 years of operation, the design of the attitude control system that continues to point the antenna at Earth. Every one of these decisions is encoded in the physical object now moving through interstellar space. The people who made the decisions are gone, but the decisions persist, operating, producing results, contributing to science. And the golden record. Andrewian's brainwaves recorded while she thought of love and the history of the world. Her thoughts, a specific series of electrical potentials in a specific human brain on a specific afternoon in 1977, translated into a waveform and pressed into copper, and now flying through interstellar space. She is still alive. The thoughts she thought that afternoon are older than most of the people who will read these words. They are in interstellar space. This is not poetic license. This is physics and engineering producing something that has no precedent in the history of human civilization. The externalized inner life of specific people, their curiosity, their choices about what matters and what is beautiful, persisting in the physical universe beyond the boundaries of the solar system. This is Voyager's deepest legacy. Not the scientific data, though that is immensely valuable. Not the engineering achievement, though that is extraordinary. But the evidence that human beings, given the opportunity, will reach as far as they possibly can. And when they reach, they will carry with them not just instruments and power sources and computers, but music and heartbeats and greetings, and the electrical activity of a human mind thinking about love. This is who we are when we are trying to be our best selves. Voyager 1 is out there right now carrying all of this. Still flying, still transmitting, still the loneliest and most remarkable object our species has ever made. Go outside tonight. Find the constellation Ophiuchus, low in the south on summer evenings near Scorpius and Sagittarius. Look in that direction. Voyager 1 is out there. Not metaphorically, not as a concept. Physically, right now, a spacecraft is moving through interstellar space in that direction, at 17 kilometers per second. 23 billion kilometers from the Sun, more than 22 light hours away. The light you see from those stars left them hundreds or thousands of years ago. The signal from Voyager left it about 22 hours ago and is arriving at a 70-meter antenna in Goldstone or Madrid or Canberra right now, or will in the next few hours, or did a few hours ago, while you were sleeping, while you were working, while you were not thinking about it. It does not care whether you are thinking about it. It just keeps transmitting. In September 1977, a rocket left Cape Canaveral carrying an 825-kilogram spacecraft with a 70-kilobyte computer and 3 plutonium power sources and a 3.7-meter antenna and a gold-plated copper record. It flew past Jupiter in 1979, saw volcanoes on Io that no one had known were there, saw the cracked ice of Europa and implied an ocean beneath, changed what we understood about what kinds of worlds could be alive. It flew past Saturn in 1980, made its sacrifice for Titan, gave up Uranus and Neptune so it could pass close enough to measure the thick organic atmosphere of that strange moon. The sacrifice was worth it. Then it turned upward above the plane of the solar system and kept going. In 1990, on Valentine's Day, it turned its cameras backward one last time, took a photograph. In that photograph, Earth appeared as less than 1 pixel, pale blue, suspended in a scattered ray of sunlight. Carl Sagan wrote about that photograph words that have outlasted him, about the pale blue dot, about the mote of dust suspended in a sunbeam, about our responsibility to the only home we have ever known. Then the cameras were turned off. They have not been turned on since. Voyager kept going. In 2004, it crossed the termination shock, where the solar wind begins to slow against the pressure of interstellar space. In 2012, it crossed the heliopause, where the solar wind stops entirely and interstellar space begins. The first human-made object to do so. It measured the interstellar magnetic field. It measured the galactic cosmic rays arriving from every direction, unfiltered by any heliospheric protection. It measured the density of the plasma between the stars. It sent this data home across a 22-hour signal delay to a 70-meter antenna, receiving a signal with less power than 2/10 of 1/billionth of a watt. In November 2023, a cosmic ray hit the computer and corrupted the memory, and the data stopped making sense. For months, the spacecraft transmitted and could not be understood. A small team at JPL worked through it, reading documentation from 1977, consulting retired engineers in their 80s, sending diagnostic commands, and waiting 44 hours for each response. In April 2024, they restored it. There were tears in the control room. Because this machine that was built before most of them were born, that was flying before their parents met, that had done more in its lifetime than any other spacecraft in history, was speaking again, was still there, was still going. Right now, on that spacecraft, 4 instruments are running. A magnetometer measuring the galaxy's field, a plasma wave detector listening for disturbances in the thin interstellar gas, 2 cosmic ray detectors counting the high-energy particles that bombard it from across the galaxy. This data is being formatted by a 70-kilobyte computer, being transmitted at 23 watts toward a moving target 22 light-hours away, arriving at an antenna the size of a 23-story building and being amplified from a signal smaller than the smallest imaginable trickle of power into something a human can read. And on the outside of that spacecraft, an aluminium case. Inside the case, a gold-plated copper record. On the record, 90 minutes of music from 27 cultures. Bach and Mozart and Chuck Berry and Azerbaijani mugam and Bulgarian folk singing and Senegalese drums. The sound of surf and rain and thunder and wind and whales. A newborn's cry, human laughter, a heartbeat, greetings in 55 languages, the brainwaves of a woman thinking about love. This record will last more than 1 billion years. The sun will have burned out, the earth will be gone, the human species will be whatever it has become or ceased to exist. The record will still be there, still in interstellar space, still carrying the music we found beautiful and the voices that said hello. and the electrical patterns of a human mind on a particular afternoon in 1977. The most durable artifact our civilization has ever created. Not the pyramids, not any cathedral or library or monument, a gold-plated copper disc flying through the space between stars. Look toward Ophiuchus. It is out there, right now. The signal is on its way. In 22 hours, it will arrive at a dish in California or Spain or Australia, and someone will read the data, and the spacecraft will have spoken one more time across the longest distance any human message has ever traveled. This is what we did with our first opportunity to send something beyond the solar system. We sent science, and we sent engineering, and we sent a 70 kilobyte computer that has now worked for 47 years. And we sent music, and we sent a heartbeat, and we sent greetings in 55 languages from the inhabitants of a pale blue dot to whoever might be listening in the dark. 47 years, 23 billion kilometers, still going. Go inside, but remember that direction, toward Ophiuchus, toward the space between the stars. That is where we reached.